Welcome everyone. You are joining us for Medical Laser Applications, defining measurement solutions that keep the process on track. This webinar is presented by Ophir and hosted by us at Photonics Media. Today you're going to hear from Mark Slutzki. He is the Product Manager for Power and Energy Measurement Solutions at Ophir. In this session, he is going to share the process for identifying and configuring the appropriate monitoring and measuring solutions, as well as approaches to implementation. You can ask questions or leave comments in the chat box at any time. If you have any technical issues during the event, please log out and back in to rejoin. You will be able to access the recording of this online after the event, and you will receive a link to that recording in your email inbox. So with nothing further from me, I'd like to welcome Mark Slutzki. Welcome.
Thank you, Joanna, and hello everyone, and thanks for joining us. I have to say this is really one of my favorite topics that I like discussing, and soon you'll hear and see why I'm saying that. Okay, January 19th, 2006, NASA launched a space probe called New Horizons to be the first probe to do a close flyby and study of what was then still classified as the planet Pluto. Poor Pluto didn't realize that just half a year later it would be demoted from planet to dwarf planet. To this very day, there are still arguments among the International Astronomical Union about that. All I can say is, happy is the person who that's what keeps them arguing for 10 years, but okay, I'm being a little bit facetious. About a year later, February 2007, New Horizons passed by Jupiter at just such a distance, just such an angle, just such a velocity that it got a gravity assist, which flung it in this direction, gave it quite a bit of acceleration so that it got to that spot exactly when Pluto got to that spot. The increased velocity saved about 2 or 3 years of flight time. By the way, no laws of physics were violated. Jupiter lost the same momentum that the spacecraft gained, except because of the differences in mass. Jupiter is slowed down by something like 10 to the negative 21 kilometers per hour, something like that. So I don't think it'll have much to complain about over the course of its lifetime. July 14th, 2015 was the moment of closest approach. New Horizons flew just 12,500 kilometers above Pluto's surface, took some incredible pictures, made measurements. So 9.5 years of flight time, 5 billion kilometers distance, and not just a straight line, but a very complex trajectory, including that gravity assist. And now hold on to your seats. The moment of closest approach occurred within 1 minute of the originally calculated plan that had been, figured out 10 years earlier. Within 1 minute. The science and technology work because they're based on numbers, and those numbers come at the end of the day from accurate measurements. Aha, now we know why I'm saying all this. So we'll use that as our introduction. Now we're going to be looking at medical and aesthetic applications of lasers, and we're going to be focusing on monitoring laser performance. Now this topic is in a sense kind of wearing a costume, because what I'd really like to do is I want to map out the thought process that we're going to use to identify and configure the appropriate monitoring and measurement solution for any given application, the most intelligent approach to implement it. And as we'll see, it's usually not at all trivial. I'd like to hold up that algorithm, if you will, as a model. In fact, that same algorithm will work in any other application with only technical details that are going to need to be translated. So whether it's laser cutting in, automotive manufacture, additive manufacturing, via hole drilling in semiconductor production, PV dicing, from the perspective of monitoring the laser to make sure the process stays on track, there's no real fundamental difference between these. So in other words, what we're going to do is we're going to look at how we go about defining a laser process monitoring and controlling solution using medical applications as our reference application. But having in mind all along that the thought process is really common, more or less, to many other laser-based applications as well. So we'll begin with the beginning, and we'll do a quick overview of medical and aesthetic laser applications, just see what their nature is very, very briefly. What we're essentially doing in the typical laser-based medical application is we're using the power delivered by a laser beam to zap tissue. And the differences between applications are in the details of what type of tissue and what kind of zapping we're going to do. And from those considerations, we're going to derive all the details of the process, the wavelength of the laser, how much power or energy, whether we need a continuous beam or a pulse beam, the delivery method, and so on. So obviously, if we're going to be cutting into heart muscle or doing a dental procedure or corrective eye surgery, we're going to be using very different levels of brute force in each of these different applications. Now, besides applying the power of a beam to a human patient, we can also use the power of the beam to produce medical devices. Sometimes this sort of thing is also considered medical for regulatory purposes. We're going to come to that momentarily. So for example, we can use a laser to produce things that we otherwise would have a very difficult time doing, such as this stent that you see here, or a pacemaker, or devices for, implantable devices for controlled release of a drug inside the body, and so on. There's also a whole class of applications that we're going to call aesthetic, by which we loosely mean a procedure whose primary purpose is to improve appearance rather than improve function. It may or may not be medical in nature. So some types of skin treatment, now obviously there are some that are definitely medical, but there are some skin treatment applications that aren't there to solve a medical problem, but are there to improve appearance, to improve quality of life, hair removal, tattoo removal, things like that. And as we'll see soon, at least from a regulatory point of view, there are going to be some differences. Well, let's pose that as a question, actually. What is the difference whether I define something as a medical application or aesthetic but not medical? So that brings us to the more general issue of regulatory questions. If I'm designing a laser-based, cutting machine for industrial production, the legal authorities are really not going to take much interest in whether it works well or not. That's a financial risk that I'm taking, or that the customers are taking. But when it comes to medical applications, the legal authorities do get involved, and the degree to which they get involved and the nature of the demands that they're going to place depends on the degree and the nature of the risk that the system in question poses to the patient. So when we're talking about a laser-based system, then as you can realize, it's a function of how much power is in the beam, the power density in the plane at which the patient is going to meet this beam, how long that's going to happen for, the exposure time, and so on and so on. Various laser parameters that affect the degree to which this beam is dangerous. A very high power beam, but inside an enclosed system to which the patient can't reach, might be less dangerous than a moderate powered beam that the patient is able to access. Still in our overview, measurement instruments to monitor the laser performance show up at all levels of the supply chain, starting at the engineers and scientists working in an R&D environment, developing the processes, production personnel performing quality control testing at the end of a production line, who might need way fewer functions in their measurement device than the engineers and scientists in R&D did. They're just measuring two, let's say, specific parameters that the QC is interested in over and over and over again. You might have a measuring instrument integrated inside a host system working autonomously, field service engineers that are running around the world servicing the instruments that the manufacturer has sent out there, carry with them a toolkit in which they'll have measurement instruments suitable for the work that they're going to need to do, and so on. Okay, let's take a moderate dive into the process of how we go about defining our monitoring solution. And we're going to map this out in several steps. So let's begin with step 1, or step 1A. We'll see momentarily why I have a 1A. There's clearly going to be a 1B. And you'd be surprised at how often even seasoned, experienced laser professionals sometimes shortcut this step. And that is defining which parameter or parameters I want to measure. I want to measure the laser power, instantaneous power, energy per pulse in a repetitively pulsed beam, spatial profile, temporal, and so on. So it doesn't take too much thought to realize that the parameters that we want to measure are going to be those key parameters, parameters that actually make the process happen. Or maybe we can say this more accurately, that make the process happen correctly. Those are the ones that we want to watch and keep our eyes on. So looking at a few specific and pretty typical non-medical applications, just to give the idea some shape, cutting, laser cutting, drilling in industrial applications, what makes the process happen is, if I can oversimplify a little bit, the power density in the focal spot. I take a beam of such and such power, focus it down to a small spot, and inside that spot, the power density is high enough to zap the material that I'm working on in the way that I want to zap it. That's not the only parameter. Beam shape, the spatial profile, is also going to be significant here because it affects the focusability, I don't know if there's such a word, and also the shape of the final spot inside of which the work is going to happen. And that could often make the whole difference between a good part and scrap. We might prefer, rather than measuring power density in the focal spot, we might prefer to measure just the total power. And we're going to want to do that, by the way, outside the focal plane, because inside the focal plane, I might cut, weld, drill my measurement device. It's the same number of watts and joules outside focus as in focus, right? Keep that in mind. So I might prefer to measure power rather than power density. It's easier, and assuming that we know, and this is a big assuming, but assuming that we know exactly what the beam shape in the focal spot will be, measuring the total power in the beam might give me enough information to tell me what I need to know. Welding is typically done using pulse beams, and there you just substitute the word energy for the word power in all the past couple of sentences, and you'll get the same idea. Just to keep things a little interesting and cool, military applications. So here you see an image from a Boeing technology demonstrator test. I believe this was 2011, using a 1 kilowatt beam to bring down a small UAV. Nowadays, for bringing down more heavy-duty targets, ballistic missiles, whatever, the experts all talk about needing something like 100 kilowatts and up. That used to sound like science fiction, but nowadays we all know that it isn't. For shooting down Imperial TIE fighters, I actually don't know how much power we need. You now know more or less how old I am, or at least what decade I'm from. Okay, now I want to share with you a case study. A customer of ours, this actually was about 15 years ago, I believe. This is on our website, because I think this will be a good illustration. Medical device manufacturer. They manufacture, among other things, this particular implantable device. I have no clue what it is. They were producing this, maybe they still are, simultaneously at 2 separate plants. Strangely, the parts coming out of one plant were fine. The parts coming out of the other plant had a high degree of failure due to faulty welds, laser welding, okay? And luckily, the flaws were all found at inspection and not, God forbid, inside a patient. But they couldn't figure out what was going on because in both plants, the setup was the same, the process was the same, the equipment, the lasers, everything was supposed to be 2 identical production lines, and yet one was producing good parts and the other one was producing scrap. They asked us to help them out. Indeed, the processes really did look the same. When we started taking measurements, when we measured, and the powers were the same, or the energies, when we measured the beam profiles of the 2 production lines, we found the difference, that the 2 beam profiles were not the same. Something in the optical delivery chain had obviously shifted out of alignment in that second plant, and that's what was causing the scrap, because the beam shape and therefore the focal spot shape and therefore the weld were not as they were calculated to be. In the perfect 2020 vision that we tend to have when we're using hindsight, we can say that in this case, beam profile should have been part of the answer to step 1A. What parameters make my process happen correctly? Beam profile being incorrect was causing a lot of scrap. Step 1B, so we just discussed what parameters. Now we want to talk about what time constants of unwanted drifts am I trying to catch. There's slow drift, the gradual degradation over a long time that happens to all instruments that are made of matter. By the way, it happens to all people made of matter as well. We don't like to talk about that sort of thing. Or are we looking for fast unwanted changes, unwanted fluctuations, if there's a reason to suspect that a given system might have those? So step 1A and step 1B together are going to help us determine what measurement technology to use. Fast detectors, low power, slower detectors, and so on and so on. And it's going to also guide the choice of implementation. How often do I want to take these measurements? Maybe ongoing real-time adjustments of fluctuations, a feedback loop, or maybe once every X months, just to check that there isn't any degradation that's reached a point where I need to do some preventive maintenance. So for example, laser diode degradation comes in two flavors. There's the gradual slow degradation, which we call wear out. That's caused by things like, slow growth of defects in the crystal, oxidation on the crystal facets, the crystal meaning the laser diode crystal, electrode degradation due to metal diffusion into the crystal. And then there's the sudden death kind of degradation, which we call random. Something just went wrong and the laser diode all of a sudden failed. I'm still traumatized when I was doing my third year project in my undergrad years. So we were, my partner and I were working on laser diodes, which shall we say were a pretty new technology at the time. And we had been given by a company we were working with like a box of 10 nifty new laser diodes to work with. And I think within the first week or two of our project, we killed 8 out of the 10. What do I mean we killed them? It turns out that they were so sensitive to even things like ESD, where the slight heat pulse caused by a little electrostatic discharge can warp one of the crystal facets enough that it no longer lasers. It suddenly turns into an LED, but it's no longer a laser diode. It was pretty frustrating. So those kind of things, failure of bonding to a heat sink and that sort of thing. Step 2, where do I want to perform my measurement? I can perform it externally at the target location. If it's a surgical system, then at the plane where the surgery is going to take place, not exactly at that plane. We don't want to measure in focus. We want to measure sufficiently defocused that we're not going to damage our laser power sensor. But at the target location, in the target space might be a good way to say it, or internally inside my system, maybe by splitting off a small percentage of the beam as it comes out of the laser. So we can implement this in a bunch of different ways. We can implement it as the beam comes out of the laser, periodically put a mirror in there and deflect the beam into a sensor, or permanently put a beam splitter there and continuously measure X% of the laser. In some types of lasers where there's useful rear mirror leakage, I can put a small sensor there, build that into the host system. How do I decide? So there are all sorts of considerations. So let's first of all think of the internal option. So there are a few positives to doing it that way. Because I'm only measuring a small percentage of the total beam power, if it's a surgical system with, I don't know, a 100-watt laser, but I'm only getting half a watt into my sensor, it means I can use a smaller, probably cheaper, lower power sensor. If it's a small sensor, quite possibly it'll have a faster response time, which if one of my motivations is to provide feedback control. That might be a big advantage. Because I'm only off to the side taking a little bit of the beam, I'm not interrupting it, so I can have the process keep on working while I'm doing my measurements. Sometimes, not always, but sometimes that's an important consideration. The main downside is that I'm only checking the beam near the laser. I'm not going to catch unwanted changes that are happening farther downstream, such as one component in the delivery optics falling out of alignment, messing up my beam profile. On the other hand, we can measure externally in the target space. Okay, there the big advantage is that I'm going to catch an unwanted change regardless of where it originated, because I'm looking at the bottom line. I'm looking at the space where the work is actually going to happen. But it means that I'm measuring the full power of the beam. So if it's a 100-watt laser, again, I'm going to need a sensor that can measure 100 watts, which means it'll probably be bigger. It might need cooling. It might be more expensive. It might have a slower response time, which may or may not bother me. And I can't have the process happen while I'm doing the measurement. Again, that may or may not bother me, but it's in the equation somewhere. I've seen many customers who found a pretty elegant way of combining these two and getting the best of both worlds. What they've done is they have a small sensor built inside the system looking at a small percentage of what's coming out of the laser. And that's ongoing because it's not interrupting the beam. And at the same time, on one of the side panels of the machine, of the system, they have an opening that they call a calibration port, a cal port. And inside that is a full power sensor that measures the full power of the beam, either before each procedure or once a day or whatever, depending on the details. The operator will take the handpiece of the laser system, stick it into that cal port, fire the laser. The system is going to measure the full power of the beam as it arrives in the target space, compare that to what it thinks the full power should be based on what the small internal sensor is reading, and then it automatically self-calibrates its laser drive and all the other internal parts of the system, and the ongoing measurements are looking at a small sample of the power. Once every X time, it'll compare itself to what actually arrives at the target, and it'll make its own internal adjustments. So it has that fast feedback control of the process, and it periodically resets itself so that it's correct. As a side point, we already sort of touched on this a few times in the last couple of minutes. Everyone knows, or should by now, that we want to measure power outside focus, same number of watts, same number of joules, but way fewer watts per unit area, so I'm not going to zap my sensor while I'm taking the measurements. What's less known is that, not always, but in many situations, if the choice is available, it's preferable to measure before focus rather than after focus. The beam comes to a focus and then continues past that and defocuses. All other things being equal, it's often preferable to measure before. Why is that? Because at the focal spot, depending on the power and depending on the instantaneous power, if it's a pulse beam and how long the pulses are and so on, at the focal spot, there are often losses caused by photoacoustic shockwave effects. Tell me that's not cool. In the real application, that won't happen, because in the real application, the beam doesn't continue past the focal spot because that's where the patient is. But if I'm going to measure the beam, I want to measure here, not here, because here I have a more accurate representation of the power in the beam. Here, I've lost some of that power sometimes. Okay, step 3. How do I make use of the results of my measurements? So if I need to catch fast changes, or even if it's slow changes, but I just want the monitoring to be fully automated without needing a human operator, the sensor could have a direct interface to the onboard system controller, say by RS-232 or USB or Ethernet communication or whatever. And its readings of power could be used to provide feedback control so that fluctuations in the laser power can be automatically corrected in real time. Alternatively, in some applications where the expected drifts in those critical laser parameters are slower, it might be enough for a human operator to simply place a handheld standalone power meter into the beam in the target space once a day, once a month, whatever. That would need to be worked out to verify that the power is within go, no-go limits, or once every X, just to have the system automatically self-calibrate its laser drive, or make sure that there hasn't been enough degradation over time that it's time for preventive maintenance, and so on. A specific but very common answer to steps 2 and 3 is to have an integrated measurement capability by way of an OEM sensor built into the host system. Laser-based surgical systems, for example, generally have a regulatory requirement to have an integrated measurement capability. The advantage of this sort of OEM sensor is that it gives you exactly what you need. It's tailored to your conditions, your wavelength, your power level, and so on. But the engineering effort that goes into putting together such a solution involves obviously a certain cost, time, and money. And so if we're talking about a one-off, that probably won't make sense to pursue that route. But if there's any kind of series production, even potential series production involved, that might make such an approach more than commercially justifiable. Every case needs to be considered, obviously, but it's an idea that's important to be aware of. If one goes the route of an OEM solution, there are all sorts of levels of integration that one might choose for the solution that one wants to implement. Maybe starting just with a raw detector element with or without electronics. In some cases, particularly when we're talking about large quantities and important to emphasize advanced users. There are customers who use just the raw thermal disk or just the raw photodiode element, possibly with the measured raw analog sensitivity provided, and that is the calibration that we would provide such customers for their sensors, and all the way up past detectors with built-in electronics tuned to a particular sensitivity or digital interface, all the way up to complete sensors, complete instruments with built-in electronics, and all sorts of stuff in addition. So here you see some examples of OEM thermal sensors with external electronics, with internal electronics. Here you see some customized energy sensors, pyroelectric based or photodiode based. So in LASIK, for example, one type of corrective eye surgery, the general preference is to use photodiode-based energy sensors, low energies, very short pulses, nasty wavelengths to work with. Most regular surgical applications, power levels, a couple hundred milliwatts up to many, many watts and tens of watts and higher, will use thermal sensors. Sometimes there are special requirements that really need something that's going to be designed from the ground up. So I just want to show you one example of that. This is actually one of my favorite solutions that we've done at Ophir. Medical customer, medical device manufacturer. And for this particular application, their light source is a fiber emitter, except this fiber emitter doesn't emit the beam out of the tip of the fiber the way we usually think of fiber emitters. Rather, the last 5, 6, 7 centimeters of the length of this fiber are rough polished, and the light is emitted in a cylindrical pattern from the last 5, 6, or 7, whatever centimeter length of this fiber. And the customer obviously wants to measure the total power being emitted from here before they start using this inside the body of a patient. So when this came to me, I was scratching my head. Okay, how are we going to measure this? The only solution that comes to mind is we're going to need capture a very large and very widely diverging beam. We're going to need an integrating sphere and a pretty big one. So I took this to one of my buddies in our R&D physics team. Actually, we were in the same class in undergrad. He's my go-to buddy when I need a very creative, out-of-the-box way of looking at a problem. And I showed this to him and I said, okay, what do you make of this? How would you do this? He thought about it for maybe 10 or 15 seconds, I'm not kidding. And he came up with this. I call this an integrating cylinder. the fiber emitter is inserted into a glass cuvette, which fits into an opening at one end of the cylinder. The inner surface of the cylinder has a matte gray absorptive coating, and that cylinder is the sensor. Thermal sensor, but just a very novel configuration. The customer was very excited. They've shown this solution many times at industry trade shows of their own, which is why I'm able to show you this. So I thought that was a really cool one. And I want to now show you another project that we did not end up doing, but that's no less instructive, just the same. Okay, again, different manufacturer, in this case of implantable electronic medical devices. In one of their facilities, they have something like 30 laser welding stations, and this customer wanted to measure the energy of every pulse that these welding stations emit in their welding and record all of this information for traceability purposes, so that if one day in the future a problem is found in one of their devices out there in the field, that sounds so engineering, in one of the patients, okay, and the problem turns out to have originated in a faulty weld, they'll be able to track down every other device that they made that's out there that was welded on that same station on that same day, and they can initiate preventive maintenance, very much in the interest of those patients. Okay, the measurement part of the solution here is really not terribly complicated, no rocket science here. Basically, the simple idea that is to fix a beam splitter at a particular angle at the output of each one of these welding systems, and the beam splitter sends a small percentage of the energy of each pulse into a sensor, and then the data from the sensor is collected and is fed into a central database. Okay, sounds simple enough. The customer wanted us to take care of the whole thing. Now, I understand their desire to outsource this. After all, it's not in their focus. It's kind of like a spare tire. You don't really want to have to spend time about the spare tire if you're in the business of designing and building the car. But on the other hand, from our perspective as a manufacturer of measurement instrumentation, our focus is also very limited to this. We really were not comfortable with the idea of taking responsibility for a pretty complex system that we knew nothing about. And we didn't end up doing this. So the takeaway here, I believe, is that the system designer should generally be the prime contractor, because the system designer is the one who knows what goes on in their system. Okay, I want to take a minute or two and just talk about a very common mistake that we come across a lot. And I hope nobody out there takes this the wrong way, but it's important to say this is quite typical of startups. We see this all the time. And that is, why do I need to buy a calibrated laser power meter? I can do this myself. I can order, some cheap photodiodes online. I have a team of engineers. I'm an engineer. We can put together an amplifier. What's the big deal? I can save a lot of costs on my system BOM, bill of materials. Okay, so let's see. It's not such a big deal. All right, that's true in some senses. If I'm gonna base my instrument on a low power photodiode, that might mean that I want to only look at a small percentage of the beam that's coming out, which means if I'm going to put a splitter near the laser, I'm not going to catch changes that happen farther downstream. Photodiodes are very sensitive. That's a plus and a minus. It means that if I'm measuring a beam whose power is anything more than a couple hundred milliwatts, I'm going to need to start putting quite a bit of attenuation in there, and that could introduce all kinds of anomalies. I'm going to need to account for the fact that the photodiode sensitivity is affected by temperature, semiconductor physics. It's affected by the pulse frequency if I have a pulse beam. There are going to be batch-to-batch variations if I'm ordering bags of photodiodes by the kilo. I'm going to need to calibrate for those variations. And we're talking about medical applications. In not all, but in many cases, as we saw, I'm going to need to be able to quantify the absolute accuracy with which I'm making these measurements. Now, none of this is Nobel Prize material, but the engineering hours that are going to have to go into this, one may very well find that what sounded like a quick little task turns into a whole design project that might really be taking away focus from where I want to be putting my focus. The cost that's going to be involved in solving these issues might not show up on the bill of materials, but they're very real and they could be very significant. Okay, I want to do some of the fun stuff. I want to get into share with you some common and uncommon but cool medical laser-based applications. This part is admittedly less relevant to other laser application areas than what we've been discussing until now, but there's some super interesting stuff here. I just couldn't resist including this. So when one thinks of laser-based medical applications, probably surgery is one of the first one that comes up. General surgery, slicing, dicing. Typically, those kind of applications use either YAG lasers or CO2. CO2 is still a very popular laser of choice in surgical applications where the target tissue is very close to important non-target tissue, including, for example, many laparoscopic procedures, gynecological applications. It's very shallow absorption depth, meaning very CO2 10.6 micron wavelength beam light is very readily absorbed by water, and we are, to a very large degree, water. That makes it easy to be highly specific in what tissue I'm zapping and what tissue I'm not zapping, so I can minimize the thermal risk to nearby tissues. Skin treatments are often based on laser beam systems to heat the area of skin where there's a problem, say sagging skin or wrinkles, and thereby stimulate growth of new tissue, which is going to be tighter and therefore more aesthetic. Some skin treatments, particularly skin tightening and skin resurfacing, if you're familiar with those, often use something called fractional CO2. It's a CO2-based laser, but with an added twist where it uses an array of pulsed pixel dots rather than treating the entire area at once, so that the exposure is actually a sort of reticle of dots pulsing rapidly, and then the whole array scans over the treatment area. This method leaves microscopic columns, as you can see in the diagram, of treated and untreated tissue throughout the treatment area. The idea behind this development was to shorten recovery time and reduce the risk of side effects. Measuring this is usually based on the same type of thermal-based power sensors that we use to measure regular laser beams. When I first saw this some tens of years ago, my concern was that what if the localized power density inside these dots might be locally above the absorber's damage threshold, even if the overall average power density seems okay. The truth is not that difficult to calculate it, but it turns out that the solution is very simple. As always, we want to defocus the beam. In a case like this, you don't want to defocus the beam too much because then it's going to expand beyond the aperture of your sensor. But it turns out that even a very slight defocus gives you a relative increase in the dot size that's more than enough to reduce the local power density inside the dot to the point where it's safely below the damage threshold, whereas the relative increase in the overall beam size is actually quite negligible. So that's something that we come across quite often. There's some very interesting some ophthalmic applications, many of all sorts of different lasers depending on what part of the eye we want to zap. One of the more interesting ones is LASIK. It's a type of corrective eye surgery that uses excimer lasers, very, very short pulses, short UV wavelengths, 193 nanometers typically. What's cool about this is that it's actually the 193 nanometer wavelength itself that does the work, with not much power, but a lot of energy per photon. If you remember your physics, you might remember that the shorter the wavelength, the higher the photon energy. So a lot of energy per photon. The 193 nanometer light actually breaks apart molecules wherever the light irradiates the tissue. And it's not by a thermal mechanism like in regular surgery, but it's by this high energy photon ripping apart the molecule. That's a mechanism that we call photodisassociation. And with computer control of this soft ablation of tissue, a cornea can be reshaped to a different diopter, eliminating the need for eyeglasses, for example. And all of this without having to bring a knife in to do the surgery. All sorts of other eye applications that are fascinatingly interesting. One thing to keep in mind is that 193 nanometer can also photo-dissociate other materials, such as the sensors that we want to use to measure it. So sensors need to be designed to be able to comfortably work under those conditions. Another cool application is called lithotripsy. The idea in lithotripsy is we want to pulverize kidney stones, for example, and pulverize them into a powder so that the powder grains are now small enough to be passed out of the body through regular, in the case of kidney stones, urinary channels, and we don't have to actually cut the patient open and perform major surgery. I first saw a lithotripsy system early in my career, and back then it was all done using ultrasound, acoustic pulses. The anesthetized patient would be lying in a bath of water, and very powerful acoustic pulses would be fired towards the patient's kidneys, like through their back. These acoustic shock waves pass through the soft tissue, the person's body, without doing anything. But as soon as those acoustic shock waves hit the very brittle kidney stone, they pulverize it. And whatever. Nowadays, ever since the 80s, it's done by laser, small incision laparoscopy. Very, very cool type of procedure. Mind-boggling idea. This is not quite new, but it's sort of new. Photodynamic therapy. The basic idea here is that there's a whole class of drugs constantly being developed that are activated only after exposure to a specific wavelength of light with a specific cumulative energy density, what's called dosage deposited. So if you think, for example, I don't know specific examples, but God forbid a person has cancer, as we know, the drugs that we use, the chemotherapy drugs that are used, can have nasty side effects because of their effect on healthy tissues. If assuming that there is a cancer drug that has already been made useful in photodynamic therapy type of usage, the drug would be inactive. So we administer the drug to the patient, it goes all over the patient's body, but it does nothing. Then, using a very small incision, we insert laparoscopically, it's the end of my day, a fiber. We bring the fiber up to the tumor, we illuminate the tumor, and only there the drug gets activated. So it does what it needs to do where it needs to do it, but it doesn't do anything unpleasant anywhere else in the patient. Absolutely fascinating. We also use lasers in a lot of imaging situations in medicine, and that's the list there is growing rapidly as well. Here you see a three-dimensional laser scan of a dental model. We use them to either scan and map three-dimensional maps of in the inside of body cavities or outside or whatever it is. And then we can use the results of that to do the next mind-boggling thing, and that's additive manufacturing. We're learning now how to actually grow tissues for implanting. We can grow bone, we can grow dental implants. Absolutely science fiction, absolutely science fiction. Okay, we mentioned aesthetic applications. Many of those are based on IPL, intense pulse light. Some IPLs are, yes, considered medical, but those that are intended only for cosmetic treatments are generally not. There have been efforts over the years to try to regulate IPL because of the obvious risk that it does pose to patients. So far, that hasn't happened. These are based on xenon flash lamps, generating flashes or pulses with energies typically a couple of tens of joules. I've been told that it feels like if you take a rubber band and go snap, something like that. Okay, sounds like fun. And different manufacturers have various interchangeable spectral filters to give a specific spectral profile to enable very particular applications, what tissues are affected, destroying hair follicles or breaking apart pigment molecules of a tattoo, and so on. Also, the temporal profile is often part of a specific design to give a particular behavior, depth of penetration into the skin, and so on. That accurately measuring such broad spectrum and widely diverging beams can be very tricky. And at Ophir, we've developed some interesting tools to help us characterize some of the difficult parameters of IPLs, such as this gadget, we call it the fishbowl, that we use for mapping the 3D or 2D angular distribution of an IPL source so that we can then quantify the accuracy of the subsequent energy measurements. Here you see two examples of sensors that we have for measuring IPL beams. They each use different optical tricks to enable them to fully capture and accurately measure the widely diverging beams that IPL systems generate. There are applications that are borderline medical, diagnostic instruments, or some research areas. Research is where we're going to find some of what will become tomorrow's medical treatments. So some of these research areas, flow cytometry, which measures the flow of particles suspended in a fluid. That fluid might be a jet of gas moving through the instrument. The particles might be blood cells or something like that. Spatialomics, this is cool. I just read about this a couple of weeks ago for the first time. It's the mapping of gene expression. Essentially, that means the mapping of molecular activities within a cell in 3D space, within living tissue. Measuring the genetic basis and epigenetic mechanisms of diseases, of disease processes. So for example, 25 years ago, amniocentesis, checking the amniotic fluid to find indications of a genetic problem, could only identify genetic problems with the resolution of entire chromosomes. The problems that are found that way are major and at least back then untreatable. Nowadays, though, we can spot problems with the resolution of individual genes, and many of those, if we find them, we can actually do something about them. By paying attention to the root cause of a disease, its molecular, sometimes, I'll elaborate on that sometimes in a sec, genetic basis, and not only its symptoms, this can revolutionize how we study and treat diseases altogether. And I've, over the years, come across quite a few fascinating startups that are working on exactly that. Whenever I think of cutting edge research, I can't help but remember these gems of quotes, one from no less than Lord Kelvin. There's nothing new to be discovered in physics now. All that remains is more and more precise measurement. Yeah, we know almost everything there is to know. We still need a bit more fine tuning, but we're just about there. You know, little could he have imagined. And he wasn't speaking out of ignorance, okay? Or another beauty by, again, no less than Albert Michelson, I mean, Nobel Prize, okay? The most important fundamental laws and facts of physical science have all been discovered. Again, we know almost everything there is to know. There's a bit more tweaking, but a little further, and we're going to be there. So I find that fascinating. Okay, I want to leave you with some concluding thoughts, and I now want to explain why I said at the very beginning that this is one of my favorite topics to discuss. Besides the fact that it was medical applications that actually first got Ophir Photonics historically to start expanding from just optics and coatings to photonic measurement solutions. But besides that, that's important enough. There's a sense of wonder here that I personally find especially exciting. We discover so many wonders of the universe when we study the universe numerically, in nitty-gritty detail and based on accurately measured data. And as much as this is true looking outwards, galaxies, string theory, everything in between, it's certainly no less so, I would say all the more so, when we look inwards at ourselves. And I want to give you just two examples of what I mean. The human eye contains about 127 million individual detector elements, pixels, if you will. Of those, about 7 million are daytime detectors. Because of their shape, we call them cones, and the other 100 million are called rods. The cones have less sensitivity to low light levels. They're meant for daytime levels, but they have much sharper resolution and they're sensitive to color. The rods kick in when light levels drop. They're not sensitive to color. They don't want to waste precious photons distinguishing color. They just want to see whatever we can see at the lowest light levels. And that's what we use at night. Now, one would assume that if the camera that we call the human eye has 127 megapixels in it, one would assume that the communication cable that connects the camera output to the brain where it gets processed should have in it 127 million nerve channels. Actually, it only has about 100,000. How does that work? Turns out that at the interface between the retina and the optic nerve cable going to the brain, there's an incredibly complex network of neurons interconnecting this way and that. And it took many years to figure out that that isn't just an interconnect. It actually performs a mind-boggling degree of signal processing. For example, image enhancement, increasing contrast, where a dark pixel in the scene that we're looking at is right next to a slightly less dark pixel in the scene that we're looking at. Our eyes and that neural network automatically makes the dark a little darker and the light a little lighter, only at the meeting between the two pixels, not everywhere else, so that I get enhanced contrast so that I can see the saber-toothed tiger that's hiding in the bushes, for example. So it sharpens our sense of what we're looking at. There are many famous optical illusions, you've probably seen many of them, that are based on this effect. Automatic gain control. Our eye can see over something like 12 orders of magnitude. The rods, our nighttime detectors, can be triggered by one individual photon. One photon. Now, all of this processing costs us some of the signal and some of the data. So that data reduction from 127 million pixels to 100,000 nerve channels, what we're doing is we're investing back a lot of that data and a lot of that energy back into the processing to enhance certain aspects. Interestingly, at low light levels, we don't want to invest quite as much of the energy. So our eye automatically adapts the amount of processing to the light level. Our eye goes one better. It also processes signals in time. That's how we're able to look at a dark scene at night, barely able to make out what's out there, but then a tiny movement out of the corner of our eye catches our attention. The change in time of that one pair of pixels sets off an alarm, and our brain's attention is drawn to that saber-toothed tiger that just twitched in the bushes. The data compression performed by that network of neurons and all sorts of other mechanisms takes care of all this. One of the mind-boggling things about it is all of this is done in an image processing computer the size of about the head of a pin. And the most mind-boggling part of this is that we're just born with this. Second example, and then we're going to conclude. The Human Genome Project was completed more or less about 20 years ago. The idea was to decode our production files so that we know every gene and every molecule that gets produced following the instructions in that gene. And then we could, in theory, have the ability to start trying to fix almost anything, or so we thought. Based on the range of molecules that we know are produced in all sorts of tissues in our body, it was expected that there would be around 100,000 genes in the human genome. That's the number of lines of software code that were needed to account for all the processes that we know go on in the human body. Turns out there's only about 26,000. Pretty much the same number of genes as there are in a fruit fly. It turns out that besides the software, there's all kinds of firmware in the cellular machinery that work together with the software to decide which instructions are going to be carried out and how, so we can get by with fewer lines of code to get the same number of processes done. For example, there's a gene called PAX6, which controls the formation of the human eye. I'm dreadfully oversimplifying this, I know. That same PAX6 gene in a fruit fly embryo controls the formation of a fruit fly eye. There's a whole suite of cellular machinery that controls how our genes control various processes. They control gene expression. Learning how to analyze and manipulate this epigenetic machinery opens potential doors to mind-boggling possibilities for treating and possibly preventing disease, improving health, maintaining health as we age, things we couldn't dream about until recently. You sometimes hear it said that humans are merely a bunch of molecules, no different in principle than from rocks, bacteria, intergalactic dust. That may be true in terms of material structure, but these clumps of molecules are capable of asking questions and figuring out how all those other clumps of molecules in the universe work and how to improve our existence by using that knowledge. How to improve not only our existence, but ourselves might require, I believe, other knowledge or maybe better wisdom of a different sort. I'm highly optimistic. So in summary, we looked at the process, the thought process, step 1A, which parameter or parameters are the ones that make our process do what I want it to do? Those are the ones I want to measure. What time constants of unwanted drifts am I looking out for? Where do I want to perform these measurements? How do I want to interface the measurement results back to my process to help me keep it on track? And then any special requirements that come in after that. As laser-based medical applications become ever more sophisticated, they also become ever more dependent on controlled and predictable laser processes. And as we saw, this applies equally well to other advanced applications. The realities of the medical arena are such that accurate monitoring of laser behavior is really not a luxury anymore. It's really a necessity on which such applications cannot afford to cut corners. We've seen how the application of new advanced technology and measurement devices can help designers of medical laser systems and processes to optimize and control their processes so that they can bring their solutions to market with confidence in their safety, their efficacy, and their profitability. Okay, so my throat is shot, but for a good cause. All right, so that's what I wanted to cover. And Joanna, I'll turn it back to you.
Thank you so much. Now we do have time to take a few questions before we close. Everyone, if you have not already, please go ahead and type your questions and comments into the webinar chat. All right, Mark, so the first question I have here is, how does the pulsed laser compare to the CW laser? Which is more cost effective?
Okay, the answer is that there isn't one answer. They do different things and they use different ways. So some of the examples we saw before, if the process, let's say welding, typical welding processes, we fire a laser, a pulse of given energy density and given pulse width and whatever, and then we stop and check what happens. In most surgical applications, we're cutting through tissue, so there we might want to use a CW laser. It's going to be more stable. It really depends on what we're trying to do. LASIK, that UV, using that nasty 193 nanometer wavelength inside an eye, it uses pulses, but there we don't fire one pulse, we fire a repetitively pulsed beam. So it's not really a question of cost effectiveness, it's more a question of the behavior. The shorter the pulse, the more critical the parameters can become. Very short pulses, and this is something worth mentioning, very short pulses, power, if you remember your basic engineering, power is energy per time. So if that energy is delivered in a pulse that's very short, like elastic pulse, nanosecond pulse width, so all kinds of funny things can happen in addition to the power. So I might need to take additional things into account. So the question doesn't really have a short answer, but I hope I answered it. It's not a question of cost effectiveness. It's a question of what's most appropriate for the process that I'm trying to carry out.
Perfect. Thank you. All right. This next person asked, Are CO2 and high power lasers in medical applications going to damage nearby cells?
Hopefully not. Generally speaking, these kind of surgical systems are designed by serious experts. I mean, you don't usually find small, one person. Actually, I don't even know if that's so true, but there's a lot of expertise that goes into that. So, for example, I mentioned CO2 is very readily absorbed by water, and we're to a very large extent water. So it'll get absorbed and it doesn't travel through very much distance of human tissue, but the mechanism by which it works is thermal. So I think I threw out a word like 100 watts, but I don't think we use 100-watt lasers in a surgical application, because okay, so it's not going to continue far past my target tissue, but it's going to seriously heat up the tissue. So each of these surgical processes or medical processes is generally very carefully designed so that exactly the optimal power level, exactly the optimal beam type and are in there. Obviously, there's always going to be a risk. If we're going to, cut into bone, we're probably going to need a little bit more brute force than if we're cutting into soft tissue, but then we might use much shorter exposure times, because otherwise, your question is exactly on the mark. If I use higher power for a long time, then there is going to be heat spreading out into the surrounding tissue besides my target tissue. So I'm just thinking out loud, the exposure time might be one of the parameters by which we help to control that. I don't know the highest power that shows up in a surgical application, but I would imagine that exactly because of what you're asking, I don't think anybody uses kilowatt lasers in any kind of surgery, for example. But yes, that question is a question that a designer of such a system is always going to have at the forefront of their thinking process as they design their instruments.
Wonderful, thank you. And I think that's all the time for questions we have now. But everyone, if we didn't get to your question, please look out for a reply from us later. If you do think of another question or would like to request a copy of today's slides, you can let us know by emailing webinar@photonics.com. That's webinar@photonics.com. And just a final note, this whole session was recorded. It will be available on the Photonics Media website shortly, and you will receive a link to that recording in your email. So I'd like to thank Mark Slutzki from Ophir one last time, and thank everybody here for participating today. This webinar was presented by Ophir and hosted by Photonics Media. Thank you, everybody.
Bye-bye.